My name is Eric Roots. I'm a PhD student working on the MT or magnetotelluric data with Metal Earth. I apologize in advance if I cough into the mic today. I'm just getting over a bout of the virus, so I'll try to get through this as smoothly as possible. So today I'll be showing some results of the inversion of the magnetotelluric data from the Western Superior, specifically looking at the long period data, which give us a look at some of the large scale resistivity structures in the lower crust and mantle across this part of the craton. There we go. So I'll start with a quick overview of the MT data that we have in the Western Superior, at least specifically that we used in this study. Then show some results from 3D isotropic inversion of that data. And finally, I'll talk a little bit about the possibility of electrical anisotropy in the mantle in the Western Superior and show some results from forward modeling studies that we performed. So here is the simplified geological map of the Western Superior and its surrounding areas. As you can see, we have quite the collection of stations on the map, a combination of broadband and long period or BBMT and LMT stations from the lithoprobe project in the Western Superior. Of course, we have 6 now, I believe, Metal Earth transects in this area as well, not shown fully on this map, but those would be Rainy River around here, Dryden and Atikokan through here, Sturgeon somewhere around there, and then Geraldton to the east over here, and I suppose Red Lake now up to the north. So those transects were collected with a station spacing of 5 kilometers or less, whereas the lithoprobe data has an average spacing of about 25 kilometers, give or take a little bit. So for computational purposes, it's not quite feasible yet to include all of the data in the study at this scale. So as you can see, I've only shown a few of the Metal Earth data sets, basically used for the purposes of infill in this study. You'll also see we have a large number of stations to the south. Those are from the US Array data set. We've included those partly because part of the craton sits in the US, specifically the sort of southwestern tail piece down here, but also because through performing over 50 inversions using a variety of subsets of the data set, we found that we tended to get better and more believable results when we included data from as far outside the main region of interest as we possibly could. So I'm guessing that most people here are at least somewhat familiar with the subprovinces of the Western Superior, but just a quick refresher of some of the ones that I'll be mentioning. From north to south, we have the North Caribou, Uchi terrain, as Adi talked about, English River, Winnipeg River here, Western Wabigoon, and then the Quetico subprovince will probably be about as low as I'm talking about today. So as I said, we performed over 50 inversions as part of the study. So I'll be going through the results from the preferred inversion of this data set, starting here in the upper crust. So the panel on the left again is the sort of surface geology for the entire region. And the panel on the right is showing depth integrated resistivity slice from the preferred model. So this is depth weighted resistivity from 0 to 10 kilometers. So sort of a snapshot of the upper crust. Generally speaking, the upper crustal structure in the modeled region is pretty poorly resolved due to the fact that most of the stations are long period. The site spacing is anywhere between 15 to 75 kilometers, and the model cell spacing is about 10 kilometers. So this sort of integrated slice can kind of give us a bit of a better idea of the bulk resistivity characteristics for the region than we would get if we just took a singular slice. Despite the relatively low resolution, we can still point out some broad scale first order features. And while not all of them are necessarily within the scope of the study, it's still worth going over them as being able to see the near surface geology reflected in the near surface of the model can still give us some confidence that our inversions are doing sensible things. So first off, the contrast between the craton itself and the surrounding largely sediment covered terrains comes through pretty nicely in the model. So we have this white dashed line kind of contouring roughly the craton. And you can see for the most part on the craton, the resistivities are very high, especially so to the north in the North Caribou terrain where we're getting to 10 and even 100,000 ohm meters. As we move to the south a little bit into some of the more belt-like subprovinces, we get a little bit more heterogeneity in the resistivities. West of the craton, we see sort of low to moderate resistivities reflecting some of the Phanerozoic sediment-covered places in southeastern Manitoba. And the same is true more or less in the US, where we have mostly sediment-covered terrains and low to moderate resistivities. You can see some features like a higher resistivity zone here corresponding to this volcanic dome in the US. And if you squint, maybe you can make out this sort of S-shaped resistivity feature that correlates nicely with the mid-continent rift system through here. So while the details of, or I should say the fine details of these structures are maybe not very well resolved, they do largely agree with what we might have expected just by looking at the surface geology. In addition to that, there's been a good amount of work done from researchers in the US using just the US array data set that these results largely agree with. So if nothing else, it gives us a bit of confidence that this model is doing something somewhat reasonable. So for the rest of the presentation, since we don't really have time to go through every image feature, and nor would they all necessarily fall within the things we're really interested in, for the rest of the presentation, I'll just be focusing on what's inside this black dash box here, sort of in the center of the Western Superior. So we've already covered the upper crust. We're jumping to a slice here in the mid to lower crust at 31 kilometers depth through the preferred model. And this is where we really start to see the coherent structures start to come through. So as in the upper crust, the North Caribou terrain to the north is largely resistive. To the south, underneath sort of the sub-province boundaries corresponding to the Uchi terrain, English River and Winnipeg River, and to a lesser degree, the Western Wabigoon terrain, we see this fairly prominent, I'd say, backwards D-shaped conductive feature with a little resistor in the middle. That these lie mostly subparallelly and beneath the sub-province boundaries. So we have this upper arm of the sea sitting sort of right beneath the English River subprovince, lower arm sort of paralleling the boundary between the Winnipeg River subprovince and the Western Wabigoon, and then the apex of the conductor here sort of joins up where the three subprovinces pinched together. It seems likely too that this upper arm might be what might be the sort of the low resolution footprint of the feature that Adamola talked about in his presentation. That was also imaged by Ferguson et al. In, I believe it was 2004. So that conductor continues down from the mid to lower crust down to at least 45 kilometers depth, where we also start getting another conductive feature running subparallel to the Quetico subprovince boundary for about 400 kilometers here before turning up beneath the Nipigon embayment, potentially continuing off to the east here, but we don't really have the data to confirm that right now. Before I go any deeper into the mantle depths of this model, I'd like to take a quick stop to compare the crustal features that we talked about briefly with what we saw over in the Abitibi. So on the left, again, we have that same slice at 45 kilometers from the Western Superior, and then on the right, we have a slice at 51 kilometers depth from the model that we generated over in the Abitibi. These lower crustal depths are really the primary regions of overlap between the Western Superior and the Abitibi models. One thing that stands out to me, and I'd be interested to hear if anyone sees anything different here, is the similarity between this sort of region here and what we see in the Abitibi over here, where we have an alternating sequence of linear conductive feature, resistive feature, conductive feature, similarly seen over in the Abitibi. In both cases, those linear features coincide with fairly major crustal faults, and in 3 out of 4 of the cases, they coincide with subprovince boundaries. And considering the different scales of the models, the lateral extents are also surprisingly similar, actually, with each running from 1 to 200 kilometers in sort of east-west extent and about 100 kilometers in north-south extent. In the Abitibi, this was sort of the interpretive cartoon that we came up with to explain those features, looking specifically here at the lower part of this figure, where we explained that conductor, resistor, conductor as a pattern representing alternating zones of mantle and upper or lower crust enrichment caused by slab breakoff or delamination, forcing mantle upwelling into the upper mantle here. Well, obviously, we used a lot of higher resolution MT and seismic in the Abitibi to come up with this cartoon, and that we don't necessarily have in the Western Superior, especially with regards to anything shallower than about 30 kilometers. Several studies in the Western Superior, in and around the region that we're talking about, have used gravity and seismic data to infer ductile extension and lateral crustal flow in and around that sort of Uchi, Winnipeg River, English River area. And that kind of crustal flow is also inferred from seismic data in the Yilgarn Craton of Australia, where the authors suggested that the extension may have been triggered by thermal reweakening of a perhaps over-thickened crust, associated with something like, for example, delamination of the lower crust. So there's definitely a precedent for this line of reasoning, and gives us a possible explanation for the C-shaped feature that we see in the Western Superior. So moving on now from the crust into the mantle, starting again at the slice at 45 kilometers depth, just so we remember where we're at. Moving one step deeper to 63 kilometers depth, our curvilinear subprovince following the conductors start to fade and shift a little bit. By 89 kilometers depth, the character of the model has changed quite a bit, with the largely east-west trending features in the crust morphing into these more so north-south trending features. And the transformation is more or less complete by 129 kilometers depth, where we see this series of alternating conductive resistive bands extending pretty much from the western extent of the model over here all the way to the Nipigon Bayment. And I suppose you could make the argument too for this being another one over here. The north-south extent seems to be largely controlled by the Quetico subprovince to the south, and the North Caribou to the north, although with the exception of this one feature here. Although I will say, without going into too much detail, that we don't have a lot of good data in the North Caribou to really constrain it, and the data that we do have doesn't really support the extension of this linear feature that far into the Craton core. So the alternating bands continue down to 189 kilometers depth, though there is a notable decrease in the overall resistivities as we're starting to get closer to the likely depth of the asthenosphere. And by 244 kilometers, the banding is nearly completely faded, and we have generally low resistivities throughout the region, again, consistent with estimates for the depth of the LAB in this region. So there's a lot going on, specifically at the mantle depths, including a complete 90-degree reorientation of the trends with east-west structures in the crust, those north-south structures in the mantle, seen here. Those north-south trending alternating bands run roughly from 100 to 200 kilometers depth, but these kinds of features coming through in isotropic MT inversions can also be an indication of electrical anisotropy. So anisotropy in terms of MT can be macroscopic, or basically that there are structures similar to what we're seeing in the image here, but smaller than we're able to actually image. So it could be, for instance, a series of mantle dikes of some size at the scale that we see here or smaller. Or the anisotropy can be microscopic, meaning the actual microscopic makeup of the minerals that form the mantle. For instance, the crystal of olivine itself may be sheared in such a way that it is anisotropic. And it's basically impossible to uniquely determine which of these is the case, but we can at least try to make some comparisons and run some tests to figure out which of the cases is the most likely, as that will obviously have a big effect on how we interpret things. So I believe I showed a chart like this during the last meeting from Juan and Romanowitz 2010. The left plot is the seismic fast axis direction from the superior, and the right is the magnitude of anisotropy. And you can see here that they inferred or were able to image between 100 and 200 kilometers depth that the seismic fast axis direction is roughly north-south, and that deeper than that, it turns to roughly east-west, which is approximately the average plate motion direction. So that 100 to 200 kilometer interval is sort of what we're using as a comparison for the MT, as that overlaps quite nicely with what we seem to see. However, for the seismic data, the explanation that's typically invoked for these kinds of anisotropies is the lattice preferred orientation, or LPO, of olivine crystals in the mantle, which, among other things, can be related to the deformational history of the region. Also, unfortunately, I guess, the degree of anisotropy or electrical anisotropy that is possible strictly due to LPO and mantle minerals seems to be a little bit still up for debate. So estimates on electrical conductivity and anisotropy in mantle minerals relies on laboratory studies on single crystals typically, which are quite hard to do. And the results can vary from lab to lab, but this example here shows that conductivity can increase both with increasing water content, so the plot on the left, as well as with increasing temperature, and then anisotropy can also increase with increasing temperature. However, for sort of typical asthenospheric values, which is what these boxes represent, typical asthenospheric water contents, temperatures, so on, the maximum aggregate anisotropy, so not just a single crystal of olivine or garnet, but the actual aggregate mantle anisotropy is about 3. So obviously that would be less if we're talking about things in the lithosphere. So what that means is that for LPO and olivine or mantle minerals to be the explanation for the structures we're seeing in the Western Superior, we should be able to explain the data with a mantle that has an anisotropic factor of about 3. So I ran a series of 3D anisotropic forward modeling studies to try to test that with some different setups to see what it would take to fit the data that we have. And this is about as close as I could get. So the plot on the left shows some MT data from a particular site. You can think of the x-axis here as being a proxy for depth, so increasing periods correspond loosely to increasing depths. And the y-axis you can think of as being a proxy for changes in resistivity. So phase values less than 45 mean that the resistivity is increasing with depth, vice versa. For phase values over 45 means the resistivity is decreasing with depth. And we see these curves for the 2 modes, so along the most conductive and least conductive direction. The plot on the right here shows the model or a depth profile through the 3D model beneath this station that I generated for the forward modeling studies that got the closest to matching the data. And that model goes like this. We have a crust that is the exact same as that was used or that was generated in the inversion. And that goes all the way down to about 55 kilometers, where we then have a isotropic upper mantle block of about 3,000 dome meters. At 100 kilometers depth, our resistivities in the north-south and east-west directions diverge and become anisotropic, with those in the north-south direction very quickly going to a resistivity about 5 at a depth of 410 kilometers, whereas the resistivities in the other direction stay at about 3,000 dome meters before more slowly decreasing, again to about 5 at 410 kilometers. You can see that this model fits the data fairly well. However, from the plot on the far right, you can also say or see that it required using an anisotropic ratio that approaches 60. And even that was not quite enough to match the phases at the very high end up here. So all that to say that with our current understanding of mantle mineral physics, anisotropy of sheared normal mantle minerals are not, or very likely not, the cause for the apparent anisotropy in the Western Superior. So to summarize that, we performed over 50 inversions of the data from the Western Superior. We selected a preferred model from those, and in the preferred model, we saw a fairly good correlation between the bulk resistivities in the upper crust and from the upper crustal geology, specifically high resistivities on the craton, lower ones in the surrounding sediment-covered terrains. In the mid to lower crust, we focused on a particular set of conductors and a resistor running sub-parallel to the English River and Winnipeg River subprovince boundaries and their associated faults, which were reminiscent of the features that we saw in the model that we produced for the Abitibi. We attributed that pattern to alternating enriched and depleted zones formed by mantle upwelling, caused by potentially an over-thickened crust, thermally weakened by delamination and the associated mantle upwelling. And a similar mechanism as in the Abitibi seems possible in the Western Superior. Finally, in the mantle, we saw a rotation in the trend from the resistivity structure from east-west in the crust to north-south in the mantle, where we had those alternating resistivity or alternating high and low resistivity bands at a depth from roughly 80 to 100 kilometers all the way down to about 200 kilometers depth, which would typically be used as evidence of anisotropy in the mantle. However, the degree of anisotropy required to fit the data is far too high to be explained by simple LPO and mantle minerals. And so we're left in search for an alternative explanation for anisotropy, of which I don't believe there are very many more for cratonic domains. For instance, if this was a younger terrain, we might be able to use interconnected partial melt as an explanation, less so in an old cold craton. Or we're left with the possibility that the truth is closer to what we saw in the isotropic model, where our mantle of the Western Superior is intruded by a series of fairly conductive dikes. So with that, I'd like to thank you for listening, and you'd be happy to hear any questions or suggestions that you have.
Great. Thanks very much, Eric. We have time for some questions. Chris?
Yeah, I have a question. When I was looking at your 31 kilometer depth slice, it seemed like some of the structures were coincident with the recording station. So I wonder, is there an acquisition footprint?
There almost certainly is.
Yeah.
Obviously, imperfect collection will lead to certain things. I guess the thing that you can say, at least for the prominent conductors, is that it gives me a bit of confidence that, for instance, this one here follows the terrain boundary more closely than it follows, for instance, this line of stations.
Right. Yeah. But there is some acquisition footprint in this image.
Almost certainly, yeah. There almost always will be for MT inversions.
Eric, it's Bruno. Those north-south structures in the mantle, you see this as being old structures, like Archean structures within the mantle, or would they be quite younger structures than like what is the relationship? Because we get that switch from east-west to north-south. So are we looking at older structure within the mantle, or we're looking at younger structures than what we see in the craton?
Given that the lithosphere of craton is usually seems to be about 200 kilometers thicker potentially in the Western Superior here, and usually said to be fairly resistant to changes, it would have to have been a really significant event. So my feeling is that they're Archean in age, but I'm not ruling out the fact that the mid-continent rift event here could have leaked something in to the Western Superior lithosphere, which is again why it's important to be able to really nail down whether these isotropic dike-like features are real, or if it's something just like, ideally, if it had been LPO and olivine, we could have just said that was the recording of subduction events in the Western Superior, and that would have been a bit more of a smoking gun for Archean aged events.
Okay, thank you.
Any other questions or comments?
The conductor on the far left of that diagram, does that correspond to the Superior Trans-Hudson interface?
Yes, it corresponds roughly to the boundary between those two. I suspect, because we have no data over there, obviously, but all of the stations along here in Manitoba point very strongly towards it. I suspect that it's sort of the projection of everything that's conductive west of the Superior. So it could correspond to the Trans-Hudson origin. It could also be a combination of the Thompson Nickel Belt, is quite a conductive feature off to the west, and the North American Central Plains anomaly is a few hundred kilometers away, and it's a fairly well-imaged, highly conductive crustalline mantle feature that could be kind of projecting its way into our model.
It's also unusual in that it crosses the crust mantle boundary.
Yeah, if we go here, it's present from 45 kilometers almost all the way down, which is why I tend not to interpret it too much. Like I said, I believe it's more or less just a projection of everything deep that's conductive west of the Superior, as opposed to being associated with one single feature.
Okay, if there's nothing else, thank you very much, Eric. Hope you get over your virus soon.
Thank you very much.